Hi, today I'm going to be doing problem 15.73, which states prove that the expression for x of t in equation 15.55 is a solution to the equation of motion for a damped oscillator, equation 15.54, if and only if the angular frequency is given by the expression in equation 15.56. So I've listed the three equations that were given below. So although this problem is mostly just a mathematical proof, I've gone ahead and drawn a picture of what damping force really is. So here is a graph of simple harmonic motion. I have my amplitude and my period listed, and the damping force basically means that over a certain amount of time you're going to get a lesser and lesser amplitude until the point that the spring stops its motion. So first what I've done is rewritten equation 15.54 on the top, and I wanted to show how we can derive that from the damping force expression. So we have that expression here, and then what I've done is, since we know that the viscous drag force is proportional to velocity, we can just rewrite this with the new damping force term. So I've got my derivation here, and if you can see down here, that's basically the same as the expression above for 15.54, the only difference being that I kept this negative k over m times x of t term on this side of the equation. So our first indication that we're going to want to use 15.56 in order to prove 15.55, which is shown at the top, is that both of these equations have a b term. So we know that whatever equation we want to use for omega has to have this b defined here. Another important indication is the fact that A can be redefined in this way, in which case it has the force-driven omega minus the initial omega, and that's important because of the fact that we have omega here. This is another indication that we're going to want to use this omega equation in order to define our position equation. The reason why it's important that we have these omegas here defined in our A term is because of the fact that we still have this up here that we want to be able to understand where it can be derived from. And it can be derived from the fact that our force-driven time equation is equal to our initial force times cosine of this term, which we can see is going to be very similar to what we have listed above. And essentially this equation tells us the oscillating driving force that is applied to a damped oscillator. And all of these things together point to the fact that it is important to have our force defined in such a way that we involve omega, and in order to involve omega we must have the previously defined 15.56 here. So if we don't use this equation and this equation in terms of omega in these individual terms, we're not going to come up with a correct equation.